For most of human history, gravity felt like the simplest thing in the world. You let go of an object, and it falls. You jump, and you come back down. The ground presses against your feet, reassuringly solid, as if the universe itself were holding you in place. Long before equations existed, gravity felt obvious, so obvious that it seemed almost insulting to question it. When Isaac Newton gave gravity its mathematical form in the late 17th century, he did not overturn this intuition. He perfected it. In Newton's universe, gravity was a force, an invisible pull acting across empty space. Every object with mass attracted every other object with mass. The Earth pulled the apple. The sun pulled the Earth. The moon pulled the oceans into tides. The same rule governed falling stones and orbiting planets. This unification was so successful, so precise, that for generations it felt final. Newton's equations could predict eclipses decades in advance. They could explain why planets move faster when closer to the sun and slower when farther away. They could even reveal unseen objects. In the 19th century, astronomers noticed small irregularities in the orbit of Uranus. By trusting Newton's gravity, they calculated where an unknown planet must be. When telescopes were pointed there, Neptune appeared almost exactly on cue. Gravity, as Newton described it, did not merely explain nature, it seemed to command it. But embedded deep inside Newton's picture was an assumption so natural that almost no one noticed it. Gravity acted instantly. In Newton's framework, the sun's gravitational influence reached Earth without delay. If the sun were somehow removed, the Earth would immediately stop following its orbit. There was no waiting period, no propagation, no messenger carrying the news across space. Action at a distance simply was. Newton himself was uneasy about this, but the mathematics worked and the universe appeared to cooperate. For over 2 centuries, no experiment contradicted this assumption. Then physics began to change in a way that gravity could not ignore. By the late 19th and early 20th centuries, experiments on light revealed something extraordinary. Light did not behave like sound or waves in water. Its speed was the same for all observers, regardless of how fast they were moving. This was not a matter of imperfect instruments, it was a fundamental feature of reality. From this emerged a principle that would reshape physics. No signal, no influence, no transfer of information can travel faster than light. This principle did not merely constrain electromagnetism. It placed a hard limit on causality itself. If something happens over there, the soonest it can affect over here is after light has had time to cross the distance. And gravity quietly was now in trouble. If gravity were a force in the Newtonian sense, acting instantaneously, it would violate this cosmic speed limit. The sun would be exerting influence on Earth faster than any signal could travel. The universe would be allowing one interaction, gravity, to cheat the rules imposed on everything else. This was not a small technical issue. It cut straight to the foundations of physics. The tension became clear with a simple but unsettling thought experiment. Imagine the sun were to vanish at this very moment, not explode, not dim, but simply cease to exist. According to Newton, Earth would immediately fly off in a straight line, freed from the sun's pull. But according to the finite speed of light, Earth would continue to orbit for about 8 minutes, the time it takes light to travel from the sun to Earth, before anything changed. Modern physics tells us the second picture is the correct one. Earth would keep following its familiar path, tracing a ghostly orbit around a sun that is no longer there until the information about that change finally arrived. Gravity does not act instantly. And if it does not act instantly, then it cannot be a force in the Newtonian sense. This is where Albert Einstein enters, not by adjusting Newton's equations, but by questioning the stage on which those equations were written. Einstein did not ask how strong gravity is. He asked what it really does. To understand his insight, it helps to let go of a deeply ingrained picture space as an empty container, and time as a universal clock ticking the same way everywhere. In Newton's universe, space is passive and flat. Time flows independently of what happens within it. Forces act within this backdrop, pushing and pulling objects from one trajectory to another. Einstein realized that this picture was the problem. In his view, space and time are not separate arenas. They are aspects of a single structure woven together so tightly that you cannot disturb one without affecting the other. Motion through space affects the passage of time. The presence of mass and energy alters the geometry of both. The universe is not a rigid stage. It is a responsive fabric. Once this idea is taken seriously, the meaning of gravity changes completely. Consider again the falling apple. In the Newtonian story, the apple is initially at rest, then a force acts on it, pulling it downward. The apple accelerates because something pushes it away from its natural state. But Einstein asks a different question. What if the apple is not being pushed at all? In Einstein's framework, the apple is doing exactly what it should be doing. It is moving freely, following the straightest possible path available to it. The reason that path leads toward the ground is not because Earth pulls on the apple, but because Earth has altered the geometry of the surrounding space and time. What we perceive as falling is simply motion along a curved structure. This is the twist that collapses the old belief. The apple is not being dragged downward. It is moving straight ahead through a world in which straight no longer means what it once did. The same applies to the moon. It is not tethered to Earth by a gravitational rope. It is moving freely, but the shape of spacetime around Earth bends its path into a closed loop. From our perspective, this looks like an orbit. From the moon's perspective, it is simply following the geometry laid out for it. This reinterpretation does something remarkable. It removes gravity from the list of traditional forces. There is no gravitational push or pull propagating across space. Instead, mass and energy determine the structure of spacetime, and spacetime determines how objects move. In this picture, there is nothing instantaneous. Changes in mass and energy reshape spacetime, and those changes propagate outward at the speed of light. When massive objects move, accelerate, or collide, the geometry around them responds, sending ripples through spacetime itself. Gravity obeys the same causal rules as everything else. What once looked like action at a distance becomes local geometry. This shift also explains why gravity is so universal. In Newton's theory, gravity acts on mass. In Einstein's, spacetime curvature affects everything. Even light, which has no mass, follows curved paths when spacetime is distorted. This is why starlight bends when passing near the sun, and why massive galaxies can act as lenses, warping the images of objects behind them. The collapse of Newton's picture is not a failure of his genius. His theory remains extraordinarily accurate in everyday situations and even in most astronomical contexts. Spacecraft, navigation, bridge, engineering, and planetary motion can still be calculated using Newton's equations with astonishing success. But accuracy is not the same as truth at the deepest level. Einstein showed that Newton's gravity is an approximation, a shadow cast by a richer underlying reality. Perhaps the most unsettling consequence of this realization is what it says about our own experience. We tend to think of standing still on the ground as the natural state, and falling as something that happens when gravity intervenes. Einstein turns this intuition inside out. In his universe, falling freely is the natural state. Standing still on the ground is what requires explanation. When you are standing on Earth, your body is not following its natural path through spacetime. The ground beneath your feet is pushing you upward, preventing you from moving the way spacetime geometry tells you to move. The sensation of weight you feel is not gravity pulling you down, it is the electromagnetic forces in the ground pushing you up. This reversal is subtle but profound. It marks the moment when gravity stops being a familiar force and becomes something stranger, a feature of reality itself, woven into the shape of space and time. By the end of this first collapse, one belief has already fallen away. Gravity is no longer a pull acting across emptiness. It is the visible trace of an invisible geometry, one that we inhabit, move through, and rarely notice. Once the old image of gravity begins to crack, something quietly unsettling takes its place. If gravity is not a force pulling objects downward, then what exactly is happening when you feel your weight? And more disturbingly, what is happening when you do not feel it? Our everyday intuition insists that standing still is normal. Falling is what needs explaining. We imagine rest as the default condition of matter, and motion as something imposed from the outside. But Einstein noticed that this intuition is backwards, not slightly backwards, completely inverted. To see why, imagine a situation that is uncomfortable but revealing. You step into an elevator. The doors close. The cable snaps. For a brief moment before fear has time to fully register, something strange happens. You feel light. The floor no longer presses against your feet. Objects released from your hand do not fall beside you. They float, sharing your motion. Inside that falling elevator, gravity seems to have vanished. Yet the Earth is still there. Its mass has not changed. Nothing about the surrounding spacetime has suddenly become flat, and still gravity appears to be gone. This observation was not new. Astronauts had not yet flown when Einstein was thinking, but the idea of freefall was already well understood. What Einstein realized was that freefall is not a special case. It is the key to understanding gravity itself. Inside the falling elevator, every object accelerates in exactly the same way. A hammer and a feather released together will remain side by side. Not because gravity is weak, but because gravity is no longer acting as a force on them at all. They are moving freely, following the natural paths set by spacetime. This led Einstein to a radical statement. Locally, the effects of gravity are indistinguishable from the effects of acceleration. This is the equivalence principle. To appreciate how strong this claim is, consider the opposite scenario. Imagine you are inside a sealed elevator drifting in deep space far from any stars or planets. There is no gravity. You float. Now, without warning, the elevator begins to accelerate upward at a steady rate. Suddenly, you feel yourself pressed against the floor. Objects released from your hand fall toward it. Everything behaves exactly as it would if you were standing on Earth. From inside the elevator alone, there is no experiment you can perform to tell whether you are in a gravitational field or simply accelerating through empty space. The experiences are equivalent. Gravity and acceleration are not just similar, they are locally indistinguishable. And with that realization, the concept of gravity shifts again. In Newton's world, gravity is something that acts on objects. In Einstein's world, gravity describes how objects fail to move freely. Free fall is the absence of gravitational force. Weight is what happens when that freedom is taken away. This inversion is difficult to accept because it contradicts lived experience. You feel heavy when sitting in a chair. You feel supported, stable. Surely, that is the natural state. Falling feels like loss of control, not freedom. But physics is not obligated to respect intuition. When you sit in a chair, your body is being pushed upward by electromagnetic forces in the atoms of the seat. These forces prevent you from following the natural trajectory dictated by space-time curvature. Your sensation of weight is not gravity acting on you, it is the resistance to gravity. This is why astronauts in orbit feel weightless. They are not far enough from Earth to escape its gravity. In fact, gravity at the altitude of a low Earth orbit is only slightly weaker than at the surface. The reason astronauts float is that they, the spacecraft, and everything inside it, are all falling together. They are doing exactly what the apple does when you let go of it, except nothing gets in the way. This insight strips gravity of its usual drama. Falling is not something caused by a force reaching out across space. Falling is simply what happens when nothing interferes with motion. Once this is understood, another assumption begins to dissolve, the idea that gravity must be something felt. Gravity itself produces no sensation. You feel forces when something pushes or pulls on you, when your feet press against the ground, when a seatbelt restrains you, when a wall stops your motion. But pure gravity by itself is undetectable locally. In free fall, it disappears. This is deeply counterintuitive, and Einstein knew it. But he also knew that counterintuitive ideas have a habit of being correct. The equivalence principle does more than reinterpret falling. It forces a new way of thinking about reference frames, the perspectives from which we describe motion. In Newtonian physics, there is a clear distinction between inertial frames moving at constant velocity and accelerated frames. Forces appear when you accelerate. Gravity was treated as a special kind of force, one that exists even in inertial frames. Einstein erased this distinction. In his framework, gravity is not a force appearing in inertial motion. It is a feature of spacetime itself. What we call an accelerated frame and what we call a gravitational field are two descriptions of the same underlying structure. This realization had immediate consequences. If acceleration and gravity are equivalent, then gravity must affect not just motion through space, but motion through time. Acceleration changes how clocks behave. So must gravity. If you are in an accelerating elevator, clocks at different heights tick at different rates. If gravity is equivalent to acceleration, the same must be true in a gravitational field. Time itself must be distorted. Einstein did not derive this as an abstract speculation. It followed directly from the equivalence principle, and later experiments confirmed it with extraordinary precision. Atomic clocks, placed at different heights on Earth, tick at measurably different rates. Time passes slightly faster higher up, where space-time curvature is weaker. This effect is tiny in daily life, but essential in modern technology. The satellites that make GPS possible orbit Earth at high altitude and high speed. Both effects, motion and gravity, alter the passage of time. If these corrections were not accounted for, navigation errors would accumulate, rapidly growing to kilometers within a single day. Every time your phone knows where you are, it is quietly correcting for Einstein's understanding of gravity. The equivalence principle also explains why all objects fall at the same rate, regardless of mass or composition. In Newtonian physics, this fact is mysterious. Why should a heavy object and a light one accelerate equally? The gravitational force depends on mass, but so does inertia. The two effects cancel, but only because nature arranges it that way. In Einstein's picture, the mystery evaporates. Objects fall the same way because they are not being pulled. They are all following the same space-time geometry. Their internal properties do not matter. Geometry does not care what you are made of. This universality is one of the strongest pieces of evidence that gravity is not a force like the others. Electromagnetism acts only on charged particles. Nuclear forces act only at microscopic scales. Gravity acts on everything without exception because everything exists within space-time. At this point, gravity begins to look less like an interaction and more like a rule of the game. Matter does not decide whether to obey gravity. There is no switch to turn it off. Motion happens within a curved structure, and that structure applies equally to all participants. The equivalence principle was not the end of Einstein's journey. It was the starting point. From it emerged the full theory of general relativity, a description of how mass and energy shape space-time, and how space-time shapes motion. But even on its own, the principle already overturns centuries of habit. It tells us that weight is not fundamental, rest is not natural, and falling is not failure. Falling is freedom. If gravity is not a force, and free fall reveals the true structure of motion, then what exactly is this structure we are falling through? To answer that, we must finally confront the fabric itself. Space and time are about to lose their separate identities. By the time the equivalence principle has fully settled in, gravity has already stopped behaving like anything we once called a force. Falling is no longer an effect to be explained, but a clue. Weight is no longer fundamental, but a resistance to something deeper. And with that shift, a more unsettling realization becomes unavoidable. The stage on which motion happens cannot be what we thought it was. For centuries, physics treated space and time as separate absolute backgrounds. Space was a vast, rigid container, 3 dimensions, stretching uniformly in all directions. Time was a universal river flowing at the same steady rate for everything and everyone, regardless of where they were or how they moved. Objects existed in space. Events happened in time. Forces acted within this framework, but the framework itself was untouched. Einstein saw that this picture could not survive the equivalence principle. If acceleration can mimic gravity, and gravity can affect clocks, then time cannot be independent of space. If gravity can disappear in free fall, then it cannot be something layered on top of space. The only consistent conclusion is that space and time themselves participate in physics. They respond, they change, they carry structure. What emerges from this is not space plus time, but space-time, a single unified entity in which distance and duration are woven together. In space-time, every event has both a location and a moment. You cannot specify where something happens without also specifying when. Motion is no longer a path traced through space, as time ticks in the background. It is a trajectory through space-time itself. Objects do not merely move through space-time. They exist within it, constrained by its geometry. And crucially, that geometry is not fixed. Mass and energy do something extraordinary. They alter the shape of space-time around them. This idea is often summarized by a sentence from John Wheeler. Space-time tells matter how to move. Matter tells space-time how to curve. The power of this statement lies in its symmetry. There is no privileged actor. Matter does not merely obey space-time, and space-time does not merely host matter. They define each other. To understand what this means, it helps to abandon the intuition that straight is an absolute concept. In flat geometry, the shortest path between 2 points is a straight line. But in curved geometry, straightness is replaced by something more subtle, the straightest possible path available within that geometry. These paths are called geodesics. A geodesic is not defined by how it looks on a map, but by how it behaves locally. Along a geodesic, an object experiences no sideways push, no force deflecting it. It is the natural path, the one that requires no intervention. On the surface of Earth, the shortest route between 2 cities is not a straight line on a flat map, but a curve that follows the planet's curvature. Airplanes flying long distances trace arcs that look bent on maps but are geodesics on the curved surface of a sphere. Space-time works the same way, except the curvature is not confined to space alone. Time is involved as well. When a massive object, like Earth or the Sun, is present, space-time in its vicinity is no longer flat. Distances and durations are distorted. The geodesics, the natural paths, are no longer what they would be in empty space. And this is where gravity truly reveals itself. A falling apple is not being pulled downward. It is following a geodesic through curved space-time. A satellite orbiting Earth is not being held in place by a force. It is moving along a space-time path that loops back on itself. Even a beam of light which has no mass and feels no force bends its trajectory near massive objects, not because it is attracted, but because space-time itself is curved. This is why gravity affects everything equally. It is not selective. It does not depend on charge or composition. It does not care whether something is heavy or light, solid or radiant. If you exist in space-time, you follow its geometry. This perspective transforms orbits from something mysterious into something inevitable. In Newton's universe, the Earth is constantly being pulled sideways toward the Sun, while also trying to move straight ahead. The orbit is a delicate balance between inertia and attraction. In Einstein's universe, there is no tug-of-war. The Earth is simply moving forward in space-time, following the straightest path available. The Sun's mass curves space-time in such a way that this straightest path happens to close in on itself. The Earth is not circling the Sun because it is being dragged. It is rolling along the curvature created by the Sunday. If the Sun's mass were spread out differently, space-time would curve differently, and the Earth's path would change accordingly. If the Sun vanished, the curvature would relax, and Earth's geodesic would straighten out, not instantly, but after the change propagated outward at the speed of light. Nothing about this picture requires a force acting across empty space. Everything happens locally. Matter shapes geometry. Geometry shapes motion. This also explains why gravity cannot be shielded. You can block electromagnetic fields with conductive materials. You can confine nuclear forces within atomic nuclei. But gravity is not something that passes through space. It is the structure of space-time itself. There is nothing to block. Once space-time is accepted as a physical entity, strange consequences follow naturally. Time no longer flows at the same rate everywhere. Near massive objects, space-time is more strongly curved, and the time component of that curvature slows clocks down. Two identical clocks, placed at different heights, will tick at different rates, not because one is malfunctioning, but because they are embedded in different geometries. Distances also lose their absoluteness. The length of an object depends on how it moves through space-time. Observers in different states of motion do not agree on what is simultaneous, or even on what now means. These are not measurement errors. They are features of reality. At first glance, this seems to complicate physics unnecessarily. Why replace simple forces with a four-dimensional geometric fabric that bends and stretches? The answer is that the universe itself insists on it. Every experimental test designed to probe gravity more precisely has confirmed this geometric picture. The precession of Mercury's orbit, which Newton's theory could not fully explain, emerges naturally from space-time curvature near the Sunday. The bending of starlight, observed during solar eclipses, matches Einstein's predictions exactly. The behavior of binary pulsars, the slowing of time near massive objects, and the existence of gravitational waves all follow from space-time dynamics. Space-time is not a metaphor. It vibrates, it ripples, it carries energy. When massive objects accelerate, when black holes spiral toward each other, for example, they disturb the geometry around them. These disturbances propagate outward as gravitational waves, stretching and squeezing space-time itself as they pass. Detectors on Earth measure changes in distance smaller than a proton's width, not because objects are being pulled, but because the space between them is changing. This is the universe, revealing its structure directly. Yet for all its power, space-time curvature does not feel dramatic in daily life. You do not notice time slowing when you sit down. You do not see space bending beneath your feet. The effects are real, but subtle, because Earth's mass, while enormous by human standards, is small compared to cosmic scales. This subtlety is part of why gravity was misunderstood for so long. It hides its true nature behind familiarity. But once you learn to see motion as geometry, gravity becomes something entirely different from what intuition suggests. It is no longer a mysterious pull reaching across emptiness. It is the quiet rule that all motion obeys, whether we notice it or not. At this stage, one might think the story is complete. Space and time are unified. Geometry replaces force. Motion follows curvature. But space-time has one more secret to reveal. If gravity can bend space, and if gravity can slow time, then space and time are not just linked, they are vulnerable. They can be distorted in ways that challenge the very idea of a universal present. And that realization leads to the next question. If time itself can be bent, how differently might it flow, depending on where you are? The answer will not be intuitive. Once space-time is understood as something that can curve, another consequence follows with unsettling inevitability. If space can be distorted by mass, then time cannot remain untouched. The two are not separate ingredients mixed together for convenience. They are aspects of the same structure. And when that structure bends, it bends as a whole. This is where gravity stops being merely geometric and becomes deeply personal, because it reaches into the flow of time itself. In everyday life, time feels uniform. 1 second follows another with reassuring regularity. Clocks tick in unison. Aging feels steady and unavoidable. This intuition is so strong that we rarely question it. But Einstein's framework does not permit a universal tempo. If gravity and acceleration are equivalent, and acceleration alters how clocks behave, then gravity must do the same. Time cannot pass at the same rate everywhere in a curved spacetime. This is not an abstract idea layered on top of relativity. It emerges directly from the equivalence principle. Consider again the accelerating elevator. If the elevator accelerates upward, a beam of light sent from the floor to the ceiling will arrive slightly redshifted, having lost energy, climbing upward against the acceleration. From inside the elevator, this effect is indistinguishable from gravity. The conclusion is unavoidable. In a gravitational field, clocks at different heights must tick at different rates. Time itself must stretch and compress, depending on where you are. Near a massive object, space-time curvature is stronger, and where curvature is stronger, time runs more slowly. This slowing is not psychological. It is not a trick of perception. It is built into the structure of space-time. A clock placed closer to Earth's center ticks more slowly than one placed farther away. A clock near the surface of the Sun ticks far more slowly than one far out in interplanetary space. Near a black hole, the effect becomes extreme, pushing time toward a standstill as seen from afar. What makes this idea difficult to absorb is how quietly it operates. On Earth, the difference is tiny. If you live on the ground floor of a building and another person lives on the top floor, the one closer to Earth's center ages more slowly. The difference is only about 10 nanoseconds per day, far too small to notice in daily life. And yet it is real. After a lifetime, the clocks will disagree. Biology, chemistry, and every physical process that marks time will have unfolded at slightly different rates. This is not speculation. It has been measured repeatedly using atomic clocks, so precise that they can detect time differences caused by changes in altitude of just a few centimeters. Time dilation, due to gravity, is not waiting for future technology. It is already part of experimental physics. The reason we do not feel this difference is the same reason we do not feel Earth's motion around the Sunday. Familiarity hides scale. Gravity's effect on time is subtle here, because Earth's curvature of spacetime is gentle. But gentle does not mean non-existent. The practical consequences of this effect are most visible in a technology so common that we rarely think about its physics. GPS. The satellites that enable navigation orbit Earth at high altitude and high speed. Both of these conditions affect time. Their motion causes time dilation due to special relativity slowing their onboard clocks. Their altitude places them in a weaker gravitational field, causing time to run faster compared to clocks on Earth's surface. The gravitational effect is stronger than the velocity effect, so overall satellite clocks tick faster. The difference amounts to about 38 microseconds per day. This may sound negligible, but it is catastrophic for navigation. Light travels roughly 300 meters in 1 microsecond. If GPS clocks were left uncorrected, errors would accumulate at nearly 10 kilometers per day. Your phone would place you in the wrong city within hours. The only reason GPS works is because its designers program Einstein's equations directly into the system. Every position fix is an admission that time does not flow uniformly. Every accurate map reading is a quiet confirmation that gravity bends time. This is a profound shift from the Newtonian worldview. In Newton's universe, time is absolute. It flows the same for everyone, everywhere. Forces act within time, but time itself is untouched by them. Einstein showed that this assumption cannot survive contact with reality. Time responds to mass and energy just as space does. It stretches near heavy objects and relaxes far from them. This also reframes how we think about motion and aging. When you stand still on Earth's surface, you are not merely stationary in space. You are held at a fixed position within curved spacetime. The ground prevents you from following the natural geodesic path that would otherwise carry you freely. That resistance does not just create the sensation of weight, it places you deeper in a gravitational potential where time flows more slowly. In contrast, an astronaut in orbit, though moving rapidly, is in free fall. They are following a geodesic through space-time. Despite their speed, the absence of resistance, and their position in a weaker gravitational field means their clock can tick faster than one on Earth's surface, depending on the balance of effects. Motion and gravity compete, and space-time decides the outcome. This interplay makes it impossible to speak of time without context. Asking how fast time passes is meaningless unless you also ask where and how time has become local. At this point, gravity no longer resembles anything familiar. It is not a pull. It is not a field layered onto space. It is a reshaping of the very coordinates we use to describe reality. Near mass, not only do paths curve, but moments stretch. The universe does not provide a single shared now. This realization forces a re-evaluation of causality and sequence. Events that appear simultaneous to one observer may not be simultaneous to another. Near massive objects, the ordering of events becomes observer-dependent. Time loses its role as a universal referee and becomes a participant in the game. Perhaps the most unsettling aspect is how passive this all feels. Nothing dramatic needs to happen. You do not need to fall into a black hole or approach the speed of light. Simply changing altitude changes how time unfolds for you. Sitting in a chair is enough. The planet beneath you quietly slows your aging. Yet gravity does not announce itself. There is no signal when time dilates. No sensation accompanies the slowing. You cannot feel your seconds stretching. They feel normal, precisely because every process in your body slows together. Chemistry, neural signals, atomic vibrations, all obey the same space-time rules. This universality is what makes gravitational time dilation invisible from within. Only by comparing clocks across different gravitational environments does the effect reveal itself. Time is faithful locally but inconsistent globally. As gravity bends time more strongly, strange limits appear. Near a black hole's event horizon, time dilation becomes extreme. From the perspective of a distant observer, a clock falling toward the horizon appears to slow its ticks, spreading farther apart, fading into silence. From the perspective of the falling clock itself, time proceeds normally. This disagreement is not an illusion. It is a genuine feature of curved spacetime. Here, gravity shows its most unsettling face. It does not merely influence motion. It fragments reality into perspectives that cannot be reconciled into a single timeline. The idea of a universal cosmic clock dissolves completely. By the end of this realization, gravity has taken something once considered untouchable and made it malleable. Time is no longer a background parameter. It is shaped, distorted, and negotiated by mass and motion. And once time itself is no longer absolute, another tension begins to emerge. Gravity governs the largest structures in the universe, yet its influence on time is incredibly weak compared to other interactions. You can lift an object with your hand, overpowering Earth's gravity, even though that same gravity curves spacetime and slows clocks. This contradiction is not cosmetic. It points to something deeply strange about gravity's place in nature. It binds galaxies and sculpts time, yet yields effortlessly to everyday forces. That imbalance is not a flaw in our understanding. It is a clue. And it leads to the next question. How can the force that shapes the universe be so unbelievably weak? By now, gravity has revealed itself as something far stranger than a force shaping space-time and stretching time itself. And yet, at precisely this point, an uncomfortable contradiction comes into focus. The interaction that bends space, slows clocks, and governs the motion of planets and galaxies is by every measurable standard astonishingly weak. Not just weak in comparison, but weak to a degree that borders on absurd. You encounter this paradox every day, without noticing it. Pick up your phone. In that simple action, the muscles in your hand effortlessly overcome the gravitational pull of the entire Earth. Beneath your feet lies a planet with a mass of about 6 times 10 to the 24 kilograms, a concentration of matter large enough to curve space-time and slow time itself. And yet a small biological system powered by chemical reactions in muscle fibers defeats its grip without strain. There is no struggle, no delicate balance. Gravity loses immediately. This fact is not rhetorical. It is quantitative. The electromagnetic forces binding atoms in your muscles and in the phone are so much stronger than gravity that the comparison almost defies language. Between two electrons, the electromagnetic repulsion is roughly 10 to the 36 times stronger than their gravitational attraction. Even when comparing macroscopic objects, gravity remains hopelessly outmatched at small scales. It is only because gravity always adds and never cancels that it becomes dominant on cosmic scales. This creates the central puzzle. Gravity shapes the universe, yet yields to everything else. If gravity were merely another force, this would be inexplicable. The strong nuclear force binds quarks together inside protons and neutrons. The electromagnetic force governs chemistry, light, and nearly all everyday interactions. Even the weak nuclear force, despite its name, outweighs gravity by many orders of magnitude at the particle level. Gravity stands alone in its frailty. And yet gravity alone determines the structure of galaxies, the formation of stars, and the fate of the universe as a whole. This imbalance is not cosmetic. It is not a curiosity. It points to something deeply unfinished in our understanding of nature. From a Newtonian perspective, gravity's weakness is simply a property of the gravitational constant. It is small, so gravitational forces are small. End of story. But Einstein's framework does not allow such dismissal. Gravity is not a force with a coupling strength chosen arbitrarily. It is geometry. And geometry being weak raises a different question. Why is space-time so stiff? Why does it take the mass of an entire planet to produce effects that a magnet can overcome in your hand? The paradox sharpens when you consider gravity's reach. Unlike other interactions, gravity has infinite range. It does not decay away in the same way nuclear forces do. It does not require charge. It acts on everything with energy, including light. And still, it barely registers at small scales. This combination is unique. Infinite range, universal coupling, extreme weakness. Physics has no comfortable explanation for this. One way to see how strange this is to imagine a world in which gravity was stronger by even a modest factor. If gravity were only 1 billion times stronger, stars would burn through their fuel far more quickly. Planets would collapse into denser states. Complex chemistry might never have time to emerge. A slight increase would erase the long-lived structures that make the universe recognizable. Gravity's weakness is not incidental. It appears finely tuned to allow a universe that unfolds slowly, with structure forming over billions of years, rather than collapsing instantly. But finely tuned is not an explanation. It is a description of discomfort. Modern physics approaches this problem from several angles, none of which are complete. One idea is that gravity is not truly weak, but appears weak because it is diluted. In this view, the universe may contain additional spatial dimensions beyond the familiar three, and gravity may spread into them. While electromagnetic and nuclear forces are confined to our three-dimensional space, gravity could leak outward, thinning its apparent strength. This idea is not science fiction. It emerges naturally in certain attempts to unify gravity with quantum mechanics. If space-time has extra dimensions that are compact or hidden, gravity's influence would be shared among them. What we experience as weakness would be a projection effect, not a fundamental property. In such models, gravity is strong at very small distances, comparable to other forces, but its strength is dispersed across dimensions we do not directly observe. Only at large scales does it reassemble enough influence to shape cosmic structures. This hypothesis has not been confirmed, but it illustrates the depth of the problem. Gravity's weakness is not something physicists are content to accept as given. It is treated as evidence that something essential is missing. Another way to frame the paradox is through energy scales. The characteristic scale at which gravity becomes comparable in strength to other forces is known as the Planck scale, far beyond anything we can probe experimentally. It corresponds to energies so high and distances so small that space-time itself is expected to lose its smooth structure. Below this scale, gravity is negligible. Above it, our theories break down entirely. This enormous gap between everyday physics and the Planck scale is known as the hierarchy problem. Why is gravity relevant only at such extreme energies? Why does space-time curvature remain so gentle across the vast range of conditions we observe? There is no settled answer. What makes this more unsettling is that gravity does not behave like a passive, ignorable background at large scales. It dominates the evolution of the universe. Galaxies form because gravity pulls matter together. Clusters of galaxies trace invisible gravitational wells created by dark matter. The expansion of the universe is governed by the competition between gravity and dark energy. Gravity may be weak locally, but it never turns off. It accumulates patiently over time and distance until it overwhelms everything else. This accumulation explains why gravity appears insignificant in your hand, but decisive between stars. Electromagnetic forces cancel. Positive and negative charges neutralize. Gravity has no opposite sign. There is no negative mass to balance it out. Every contribution adds in the same direction. Still, this explanation feels incomplete. It describes how gravity wins, not why it starts so far behind. The paradox becomes sharper when you recall that gravity shapes space-time itself. If space-time is the arena for all interactions, why should its responsiveness be so limited? Why does it take immense concentrations of mass and energy to produce noticeable curvature? In general relativity, this stiffness is encoded in the equations themselves. Space-time resists bending. Mass and energy act as sources, but the response is restrained. This mathematical structure works beautifully, but it does not explain its own constants. Here, gravity's weakness becomes a signpost pointing beyond general relativity. At this stage, gravity looks less like a complete theory and more like a low-energy approximation of something deeper. Just as Newton's gravity was revealed to be an approximation of space-time curvature, Einstein's gravity may itself be an approximation of a more fundamental framework in which space-time is not smooth and continuous. If space-time emerges from something more basic, its rigidity could be an emergent property rather than a fundamental one. Gravity would then appear weak, not because it truly is, but because it is the residual effect of deeper microscopic dynamics. This line of thinking connects gravity's weakness to its most radical feature, its geometric nature. Geometry is not an interaction between particles. It is a collective property, and collective properties often appear weaker than the microscopic interactions that generate them. In this sense, gravity may be more like pressure in a gas than like electromagnetism. Pressure is not a fundamental force between molecules. It is an emergent effect of countless collisions. It can shape large-scale behavior while remaining irrelevant at the level of individual atoms. If gravity is emergent, its weakness would no longer be mysterious. It would be a consequence of averaging over deeper degrees of freedom. But this idea, too, remains speculative. What is clear is that gravity's weakness is not an accident to be ignored. It is a structural feature of reality, woven into the way the universe unfolds. It allows stars to burn slowly, galaxies to assemble gradually, and life to arise in a universe that does not collapse under its own weight. Yet the same weakness creates a crisis at the heart of physics. Gravity refuses to fit neatly with quantum mechanics. Its gentle curvature resists being quantized. Its effects are too small to probe directly at the scales where quantum behavior dominates. The force that shapes the cosmos is the one we understand least at the microscopic level. This is the paradox of weakness. Gravity is everywhere, governs everything, and yields to almost anything. And the deeper this paradox becomes, the more it suggests that gravity is not just incomplete, but hiding something fundamental about the structure of reality itself. That suspicion grows stronger when we realize that space-time does not merely bend quietly under mass. It can vibrate. It can carry energy. It can ring like a stretched fabric struck by cosmic events. To hear that ringing, we must listen not to light, but to space-time itself. Up to this point, gravity has reshaped nearly every intuition we once held. It is not a force, but geometry. Not a pull, but a curvature. Not something that acts within space-time, but something that is space-time responding. And yet one last assumption still lingers quietly in the background, the idea that space-time, even if curved, is rigid. That once bent, it simply sits there frozen into shape. Einstein's equations do not allow this comfort. If space-time can curve, it can also move. And if it can move, it can vibrate. This realization transforms gravity yet again. In general relativity, space-time is not a static scaffold. It has elasticity. When mass and energy change their motion, when they accelerate orbit or collide, the curvature they produce cannot adjust instantaneously everywhere. The change must propagate. And because nothing propagates faster than light, the adjustment travels outward as a wave. These are gravitational waves, ripples in space-time itself, moving at the speed of light, carrying energy and information across the universe. The idea sounds abstract until you strip it down to its essence. Imagine space-time not as an immaterial concept, but as a physical structure. If you disturb it violently enough, it responds. Not by sending particles or fields through space, but by altering the distances and times that define space itself. A gravitational wave does not move through space-time the way light does. It is a pattern of stretching and squeezing of space-time as it passes. This distinction matters. When a gravitational wave reaches Earth, nothing is pushed in the conventional sense. Instead, the space between objects changes. Distances grow slightly in one direction while shrinking in another, oscillating back and forth. The effect is extraordinarily small, but it is real. At its strongest, a gravitational wave passing through Earth might change the length of a 4-kilometer detector arm by less than 1,000th the diameter of a proton. That such a phenomenon can be measured at all is one of the most remarkable achievements in experimental physics. Einstein predicted gravitational waves in 1916, just a year after completing general relativity. At the time, even he doubted whether they were physically real or merely mathematical artifacts. The equations allowed wave-like solutions, but the effects were so weak that detection seemed impossible. For decades, gravitational waves occupied a strange status, theoretically unavoidable. experimentally unreachable. Meanwhile, the universe continued producing them. Every pair of orbiting stars, every collapsing supernova, every asymmetric motion of mass sends gravitational waves outward. Most of these waves are faint, stretching spacetime so gently that they pass unnoticed through planets, stars, and bodies. But some events are so extreme that they imprint themselves across billions of light years. The most powerful sources are black holes and neutron stars. When two black holes orbit each other, they lose energy by emitting gravitational waves. Their orbit shrinks. They spiral closer. As they do, the waves grow stronger and faster, rising in frequency and amplitude in a characteristic pattern. This final dance ends in a violent merger, releasing a burst of spacetime distortion more energetic than all the light emitted by all the stars in the observable universe during that moment. And then the waves travel on, indifferent to what lies in their path. By the time they reach Earth, these signals have been traveling for millions or billions of years. They carry with them a pristine record of the motion that created them, unaffected by dust, gas, or electromagnetic interference. Gravitational waves do not scatter. They do not fade in the same way light does. They arrive bearing information that no telescope could capture. For a century, this information remained inaccessible. That changed on September 14, 2015. On that day, two detectors operated by the Laser Interferometer Gravitational Wave Observatory, known as LIGO, registered a nearly simultaneous signal. Each detector consists of two long perpendicular arms forming a giant L shape. Laser beams travel down these arms, reflect off mirrors, and recombine. If spacetime stretches one arm and compresses the other even by an unimaginably small amount, the interference pattern of the light changes. That morning it did. The signal lasted less than a second, but within it was encoded the story of two black holes, each more than 30 times the mass of the Sun, spiraling together and merging into one. The event occurred about 1.3 billion light-years away. The waves had been traveling since before complex life existed on Earth, crossing empty space, passing through galaxies, and finally brushing past our planet with just enough strength to be noticed. This detection was not merely a confirmation of Einstein's prediction. It was a new way of interacting with the universe. Until that moment, astronomy had relied almost entirely on electromagnetic radiation, visible light, radio waves, X-rays, gamma rays. All of these are different expressions of the same phenomenon, oscillations of electromagnetic fields. They tell us how matter shines, absorbs, and scatters light. They tell us what things look like. Gravitational waves tell us how things move. They reveal motion hidden from view. Two black holes merging emit no light of their own. Before gravitational wave astronomy, such events were effectively invisible. Now they announce themselves by shaking spacetime. This is why the detection marked the beginning of a new era. For the first time, humanity was not merely observing the universe, it was listening to it. Listening in this context is not metaphorical. The signals from gravitational wave detectors are often converted into audible sound by mapping frequency changes into the human hearing range. What emerges is a short chirp, rising in pitch as the black holes spiral together. That chirp is space-time vibrating. It is geometry expressing motion. This idea would have seemed absurd in Newton's universe. Space could not vibrate. Time could not ripple. Forces acted, objects moved, but the stage itself remained inert. General relativity removes that distinction. The stage participates. The existence of gravitational waves also resolves a subtle consistency issue in Einstein's theory. If space-time curvature responds to mass, and energy changes in curvature must propagate causally. Without gravitational waves, gravity would still risk acting instantaneously. The waves ensure that information about motion travels outward at a finite speed, preserving causality. In this sense, gravitational waves are not an optional feature of general relativity. They are required. Their weakness, however, echoes the paradox encountered earlier. The same interaction that produces the most energetic events in the universe creates effects so small that detecting them requires isolating mirrors from seismic noise, thermal fluctuations, and even quantum uncertainty. Entire buildings are engineered to remain still enough to notice spacetime moving, and yet once detected, the signals are unmistakable. As detectors improve, gravitational wave astronomy is expanding rapidly. Events involving neutron stars have already been observed, including mergers that also emit light, allowing direct comparison between electromagnetic and gravitational signals. Future detectors, both on Earth and in space, will be sensitive to waves from supermassive black hole, mergers, early universe processes, and perhaps phenomena we have not yet imagined. Each detection adds a new layer to our understanding. The masses of black holes, the distribution of compact objects, the behavior of matter at nuclear densities, even the expansion rate of the universe can be probed through gravitational wave observations. Most importantly, gravitational waves offer a direct test of spacetime itself. They allow us to examine how curvature behaves under extreme conditions where gravity is strong and dynamic. Every waveform is a measurement of geometry in motion. This matters because general relativity, for all its success, is known to be incomplete. It does not incorporate quantum mechanics. It breaks down at singularities. Gravitational waves provide one of the few ways to probe gravity in its most violent regime without relying on light or matter. They are clean signals governed almost entirely by spacetime dynamics. In that sense, gravitational waves are not just messengers from distant events. They are diagnostic tools for the theory of gravity itself, and they deepen the unsettling picture that has been building throughout this journey. Gravity is not weak because it is insignificant. It is weak because it is subtle. It operates by reshaping the coordinates of reality, rather than pushing particles around. Its effects accumulate patiently, revealing themselves only over vast distances or extreme conditions. When spacetime rings, it does so softly. But the echo carries across the universe. Now that we know spacetime can vibrate, another tension becomes unavoidable. If gravity is dynamic and universal, shaping the largest structures in existence, why does it seem to be losing a battle on the grandest scale of all? Because when we look at the universe as a whole, gravity is not pulling everything together. Space itself is expanding faster and faster, driven by something that appears to oppose gravity entirely. And whatever that something is, it does not ripple. It does not collapse. It pushes. After everything, gravity has revealed curving spacetime, slowing time, vibrating across the universe. It would seem natural to assume that gravity ultimately dominates the cosmic story. Gravity pulls. Gravity gathers. Gravity builds stars, galaxies, and clusters. Left alone long enough, gravity should draw everything back together. That expectation feels almost unavoidable. And yet, when astronomers look outward, measuring the motion of distant galaxies and the large-scale structure of the universe, they see something profoundly unsettling. The universe is not slowing down. It is speeding up. Space itself is expanding faster and faster. And gravity, on the largest scales, is losing. This is not a subtle effect, hiding in the margins of data. It is written clearly into the way distant galaxies move. In the late 20th century, observations of exploding stars, known as Type Ia supernovae, revealed that faraway galaxies are receding more rapidly than expected. Not just receding, but accelerating away from one another. The expansion of the universe is not coasting. It is being driven. If gravity were the only large-scale influence, expansion should gradually slow as matter pulls everything inward. That is what physicists expected. Instead, the opposite is happening. Something is overpowering gravity, stretching space-time itself and forcing galaxies apart, even as gravity tries to hold them together. That something is called dark energy. The name is deliberately unsatisfying. It does not describe what dark energy is. It describes what it does and how little we understand it. Dark energy does not clump like matter. It does not form structures. It does not emit or absorb light. Its presence is inferred entirely through its gravitational effect, except that effect is repulsive, not attractive. On cosmic scales, dark energy behaves like a pressure built into space-time itself, causing it to expand. As the universe grows larger, dark energy does not dilute the way matter does. Matter spreads out, becoming less influential over time. Dark energy remains constant, per unit volume of space. As space increases, the total amount of dark energy increases with it. The more universe there is, the more dark energy there is to push it apart. This behavior makes dark energy gravity's opposite in the most unsettling way possible. Gravity tries to slow expansion. Dark energy accelerates it. Gravity builds structure. Dark energy tears structure apart. And according to the best measurements, we have dark energy dominates the universe. Roughly 68% of the total energy content of the cosmos appears to be in this form. Ordinary matter, the stars, planets, gas, and dust we're familiar with, accounts for less than 5%. The rest is dark matter, which gravitates normally but does not interact with light. Gravity, it turns out, governs the details. Dark energy governs the fate. This realization forces a painful confrontation with the limits of modern physics, because dark energy was not predicted naturally by our best theories. It was discovered observationally, not derived from first principles. And when physicists attempt to explain it using the tools they trust most, the results are not just wrong. They are catastrophically wrong. In quantum field theory, empty space is not empty. Even in a perfect vacuum, quantum fields fluctuate. Particles and antiparticles appear and disappear. Each mode of a quantum field contributes a small amount of energy to the vacuum. Add them all up, and empty space should possess an enormous energy density. When physicists calculate this vacuum energy using known quantum fields, the result overshoots the observed value of dark energy by about 120 orders of magnitude. This mismatch is not a rounding error. It is the worst prediction in the history of physics. If the quantum vacuum energy were anywhere near the calculated value, space-time would curve so violently that the universe would tear itself apart instantly. Galaxies could not form, atoms could not exist. There would be no slow cosmic evolution, no stars, no chemistry, no observers. The fact that the universe exists at all means that something in our understanding is fundamentally incomplete. This crisis is known as the vacuum catastrophe. It is not merely a problem with dark energy. It is a direct collision between general relativity and quantum mechanics. General relativity says energy curves spacetime. Quantum mechanics says empty space contains enormous energy. Put the two together, and reality should not resemble what we see. And yet what we see is a universe expanding gently enough to allow structure, but persistently enough to accelerate. This forces several uncomfortable possibilities. One is that our calculation of vacuum energy is wrong, because we do not yet understand how gravity interacts with quantum fields. Another is that dark energy is not vacuum energy at all, but something else entirely. A new field, a dynamic property of space-time, or an emergent effect we have not yet identified. Some theories treat dark energy as a cosmological constant, a fixed property of space-time itself. In this view, space-time has an intrinsic tendency to expand a baseline curvature that exists even in the absence of matter. Einstein originally introduced such a term into his equations, not to explain acceleration, but to force a static universe. When expansion was discovered, he abandoned it, reportedly calling it a mistake. Decades later, the cosmological constant returned, not as a mathematical convenience, but as a candidate for dark energy. Other approaches imagine dark energy as a dynamic field that evolves over time, slowly changing its influence as the universe ages. In these models, acceleration may not last forever. Gravity might eventually regain control, or dark energy could grow stronger, leading to a future where galaxies, stars, and even atoms are torn apart as spacetime expands ever more violently. At present, observations are consistent with dark energy behaving like a cosmological constant, but the uncertainties remain large enough to leave room for alternatives. What is clear is that dark energy does not behave like any known form of matter or radiation. It does not cluster. It does not dilute. It fills space uniformly. This uniformity is crucial. Dark energy does not push objects through space. It causes space itself to expand. Galaxies are not being blasted outward by a force. The distances between them are increasing because the space-time metric is changing. This distinction mirrors the geometric nature of gravity. Once again, the deepest effects do not act on objects directly, but on the structure in which objects exist. In this sense, dark energy is not merely an enemy of gravity. It is a distortion of the same arena. Gravity curves space-time inward around mass. Dark energy stretches space-time outward everywhere. The universe becomes a battleground not of forces but of geometries. On small scales, gravity wins. Within galaxies, gravity overwhelms, dark energy binding stars together. Within clusters of galaxies, gravity still holds sway. But on the largest scales, where matter thins out and distances grow enormous, dark energy dominates. Expansion accelerates. Structures drift apart. The universe grows colder and more isolated. This scale dependence is part of what makes dark energy so difficult to grasp. It does nothing noticeable in everyday life. It does nothing within solar systems or even galaxies. Only when distances become truly cosmic does its influence emerge. It is a background effect, subtle but relentless. This brings gravity's weakness back into focus. Gravity is strong enough to shape galaxies, yet too weak to counteract dark energy across the universe as a whole. The same interaction that binds stars cannot prevent space-time from accelerating apart. This suggests that gravity and dark energy are not independent phenomena accidentally opposing each other. They are likely connected at a deep level. Both shape space-time. Both act universally. Both resist simple quantization. And both expose the tension between geometry and quantum theory. Some physicists suspect that dark energy is telling us something profound about space-time itself, that space-time has microscopic degrees of freedom, and that its large-scale behavior emerges from their collective dynamics. In this view, acceleration is not caused by a mysterious substance filling space, but by the statistical behavior of space-time at the deepest level. If that is true, then dark energy is not a new ingredient added to the universe. It is a symptom of our incomplete understanding of gravity. This interpretation echoes ideas explored earlier that gravity may be emergent, not fundamental. If space-time itself emerges from more basic quantum information, then its large-scale expansion could reflect properties of that information rather than a traditional force. But again, these ideas remain speculative. Observations constrain what dark energy can be, but do not yet reveal what it is. What makes the situation especially unsettling is that dark energy dominates the future. As time passes, galaxies outside our local group will drift beyond the observable horizon. Their light will never reach us. The universe will become emptier, darker, more isolated. Gravity will continue to bind local structures, but the cosmic web will dissolve. In this sense, dark energy is not just an enemy of gravity. It is an enemy of connection. It erases large-scale relationships, leaving isolated islands of matter adrift in an ever-expanding space-time. Yet gravity does not disappear. It remains active where mass is concentrated. And in the most extreme regions of space-time, near black holes and at the earliest moments of the universe, gravity becomes overwhelming, not weak. It drives curvature to its limits. where time slows to a crawl, and geometry itself threatens to break down. That contrast hints at something crucial. Gravity is weak almost everywhere, but infinitely strong somewhere. And where it becomes strong, our theories fail. Dark energy shows us gravity losing on the largest scales. Black holes show us gravity winning too decisively on the smallest. Between these extremes lies a gap in understanding that no existing theory can bridge. And that gap points directly to the next problem gravity creates for us, places where spacetime is forced into configurations so extreme that the equations themselves return infinities and stop making sense. Those places are not theoretical curiosities. They exist, and they sit at the centers of black holes, where gravity pushes spacetime beyond its breaking point. By the time gravity leads us to black holes, it has already overturned every comfortable idea we once held. It is no longer a force, no longer gentle geometry, no longer even a subtle influence spread thinly across the cosmos. In black holes, gravity becomes absolute. Spacetime is no longer merely curved. It is driven to an extreme, where the very language of geometry begins to fail. This is not a dramatic flourish. It is a precise, mathematical statement. Black holes mark the boundary where our best theory of gravity stops making sense. A black hole forms when gravity overwhelms every other influence. When a massive star exhausts its nuclear fuel, nothing remains to counteract its own gravitational pull. The star collapses inward, compressing more and more mass into a smaller and smaller region. As this happens, spacetime around the collapsing object becomes increasingly curved. Paths that once allowed light to escape begin to tilt inward. Eventually, a surface forms beyond which no path leads back out. This surface is the event horizon. The event horizon is not a solid barrier. It is not made of matter. It is a geometric boundary in space-time. Once crossed, every possible future path points deeper inward. Light does not fail to escape because it is weak. It fails because space-time itself is oriented inward. To escape would require traveling backward in time, which is forbidden by the structure of space-time. From the outside, a black hole appears deceptively simple. It can be described entirely by a small set of properties, mass rotation, and electric charge. All other information about the matter that formed it seems to vanish from view. This simplicity is not comforting. It is suspicious. It suggests that something fundamental is being hidden. But the true crisis lies not at the horizon, but at the center. According to general relativity, continued collapse does not stop at the event horizon. There is no internal pressure strong enough to halt it. The equations predict that all the mass collapses to a single point of zero volume and infinite density. This point is called a singularity. At a singularity, space-time curvature becomes infinite. Distances shrink to zero. Time, as defined by the theory, ceases to behave meaningfully. The equations that describe gravity stop giving finite answers. They return infinities. This is not merely an inconvenience. In physics, an infinity is not a result. It is an admission of failure. It means the theory has been pushed beyond its domain of validity. Einstein himself was deeply troubled by this. General relativity was constructed to describe smooth, continuous spacetime. Singularities represent a breakdown of that smoothness. They are places where the assumptions of the theory no longer apply. The theory predicts its own collapse. This is why singularities are not considered physical objects in the usual sense. They are signals. They tell us that something essential is missing from our description of nature. To understand how radical this is, consider what general relativity normally does. It replaces forces with geometry. It explains motion through curvature. It handles black holes, gravitational waves, time dilation, and cosmic expansion with extraordinary precision. And yet, at singularities, it produces nonsense. That contradiction cannot be ignored. The problem is not limited to black holes. A similar singularity appears when we extrapolate the equations of general relativity backward to the beginning of the universe. The Big Bang, in its simplest description, is also a singularity. Density infinite, curvature infinite, time undefined. The universe begins in a state where our equations do not work. This repetition matters. It tells us that singularities are not rare anomalies. They arise precisely where gravity becomes strongest. Wherever spacetime curvature is pushed to its limits, general relativity breaks down. The question then becomes unavoidable. What is spacetime made of? General relativity treats spacetime as continuous, infinitely divisible. You can zoom in arbitrarily far and still describe curvature smoothly. But quantum mechanics teaches a different lesson. At very small scales, nature is discrete. Energy comes in quanta. Fields fluctuate. Uncertainty is unavoidable. Trying to combine these two pictures leads directly to singularities. When continuous geometry is forced into regions of extreme density, it demands infinite curvature. Quantum mechanics, however, strongly suggests that infinities are unphysical. They usually indicate that a classical approximation is being used where quantum effects cannot be ignored. This strongly implies that space-time itself must have a microscopic structure. The smooth fabric, described by general relativity, is likely an approximation valid only at large scales. Near singularities, that approximation fails. Black holes, therefore, become laboratories for quantum gravity. Even though we cannot probe their interiors directly, they expose the limits of our theories by their very existence. Another unsettling feature of black holes deepens the crisis information loss. When matter falls into a black hole, all details about its internal state appear to be erased from the outside universe. Quantum mechanics, however, insists that information cannot be destroyed. This tension leads to the black hole information paradox, one of the deepest problems in theoretical physics. General relativity suggests that information disappears behind the horizon, never to return. Quantum mechanics forbids such disappearance. Both theories are extraordinarily successful in their own domains. They cannot both be correct in this regime. This is not a technical dispute. It strikes at the consistency of physics itself. Some approaches attempt to soften the singularity by introducing quantum effects. Instead of collapsing to a point of infinite density, matter might reach a maximum density and rebound or spread into a highly compressed but finite state. In these scenarios, singularities are avoided, replaced by new phases of space-time behavior. Other approaches suggest that space-time ceases to be meaningful, at the smallest scales replaced by networks of quantum relationships or discrete structures. Geometry in this view emerges only at large scales, much like temperature emerges from molecular motion. Singularities would then mark the edge of geometric description, not physical reality. There are also ideas that black holes encode information on their horizons rather than at their centers, hinting that space-time volume may not be the fundamental carrier of information. These ideas point toward a radical restructuring of how gravity, space, and information are related. What unites all of these efforts is the recognition that general relativity, for all its elegance, is incomplete. Black holes are not just exotic objects, they are stress tests. They push gravity to its breaking point and show us exactly where the cracks appear. It is important to emphasize what this does and does not mean. It does not mean that Einstein's theory is wrong. General relativity has passed every experimental test thrown at it. It predicts black holes accurately in terms of their external behavior. It describes gravitational waves from black hole mergers with astonishing precision. But it does mean that the theory is not final. Black holes sit at the intersection of gravity, quantum mechanics, and space-time structure. They are places where all the central ideas of modern physics collide. And at that collision, something gives way. In that sense, black holes are not failures of understanding. They are guides. They tell us where to look next. The presence of singularities is gravity's way of pointing beyond itself. They signal that spacetime, as we currently describe it, is not fundamental. There is a deeper layer of reality that we have not yet uncovered. And that deeper layer must reconcile two incompatible demands. It must reduce to smooth spacetime and general relativity at large scales, while obeying the probabilistic discrete rules of quantum mechanics at small scales. Finding such a framework is one of the central goals of modern physics. Until then, black holes remain paradoxes made real. They are regions where time slows, space collapses, information hides, and equations fail. They are not just objects in the universe, they are boundaries of knowledge. And beyond those boundaries lies the unresolved conflict that has haunted physics for nearly a century, the clash between gravity and the quantum world. That clash does not stay confined to black holes. It follows gravity everywhere it goes, demanding a theory that can describe spacetime itself in quantum terms. And that demand leads directly to the next struggle. Gravity forces upon us the attempt to reconcile it with the rules that govern the smallest pieces of reality. By the time gravity reaches the quantum world, it is no longer mysterious in a poetic sense. It is mathematically incompatible. Everything that made gravity elegant on cosmic scales becomes a liability at microscopic ones. And everything that made quantum mechanics successful becomes poisonous to spacetime. This is not a gap in knowledge that can be closed with better instruments. It is a structural conflict between the two pillars of modern physics. General relativity and quantum mechanics are each extraordinarily accurate where they apply. General relativity describes planets, stars, galaxies, black holes, and the expansion of the universe with precision that has never failed an experiment. Quantum mechanics governs atoms, particles, radiation, and fields with unmatched predictive power. Each theory is internally consistent. Each has been tested relentlessly, and yet when forced to operate together, they break each other. The reason lies not in technical detail, but in worldview. Quantum mechanics describes reality as probabilistic and discrete. At fundamental scales, physical quantities do not take smooth values. Energy comes in packets. Fields fluctuate. Outcomes are not determined until measured. Uncertainty is not a flaw in measurement, but a property of nature itself. The universe at its smallest scales behaves like a restless sea of possibilities. General relativity describes reality as geometric and continuous. Spacetime is smooth, differentiable, and deterministic. Given a distribution of mass and energy, the curvature of spacetime is fixed. Given that curvature motion is determined, there is no randomness in the equations themselves. Uncertainty enters only through incomplete knowledge, not through the structure of the theory. These two pictures do not merely differ, they contradict. Quantum mechanics assumes a fixed background in which fields fluctuate. General relativity says there is no fixed background. Spacetime itself is dynamical. Quantum mechanics treats time as an external parameter that flows uniformly. General relativity says time is local, malleable, and inseparable from space. Quantum theory relies on probabilities evolving in time. General relativity reshapes time itself. When physicists attempt to apply quantum rules to spacetime curvature, the mathematics explodes. Calculations produce infinities that cannot be renormalized away. The smooth fabric of spacetime cannot be treated like another quantum field without tearing the theory apart. This is not a minor inconsistency. It means that our description of reality fails precisely where gravity is strongest and scales are smallest, inside black holes and at the beginning of the universe. At those extremes, neither theory can stand alone. General relativity predicts singularities. Quantum mechanics cannot tolerate them. The universe forces us to confront a domain where both theories are necessary and neither is sufficient. This is the problem of quantum gravity. The phrase sounds modest. It is not. It represents the search for a framework in which space-time itself has quantum properties, where geometry fluctuates, where curvature is no longer continuous, and where gravity obeys the same principles as all other interactions. One intuitive way physicists approach this problem is by analogy. Electromagnetism, once mysterious, was eventually understood as a quantum field, with particles, photons mediating the interaction. The strong and weak nuclear forces are described by similar quantum fields with their own carrier particles. If gravity is to be treated on the same footing, it too should have a quantum carrier, the graviton. The graviton would be a massless quantum particle that transmits gravitational interactions analogous to the photon transmitting electromagnetic interactions. In weak field approximations, when spacetime curvature is small, gravity can indeed be described mathematically as if it were mediated by such particles. In this limit, the theory behaves like a conventional quantum field theory. But this success is deceptive. Unlike electromagnetism, gravity does not live in spacetime. It is spacetime. Quantizing gravity is not like quantizing a field on a background. It requires quantizing the background itself. When gravitons interact strongly, they do not merely exchange energy. They alter the geometry on which the theory is defined. The framework begins to eat itself. This self-referential problem is why a simple graviton theory does not solve quantum gravity. It works only where gravity is weakest, precisely where it is least interesting. To move beyond this, physicists have pursued more radical ideas. One major approach is string theory. In this framework, the fundamental objects are not point particles, but tiny vibrating strings. Different vibrational modes correspond to different particles. Gravity emerges naturally because one of the allowed vibrational states behaves exactly like a graviton. Crucially, string theory requires extra spatial dimensions beyond the familiar three. Gravity's weakness may then be explained by its ability to spread into these hidden dimensions, while other forces remain confined. String theory has mathematical elegance and unifying power. It brings gravity and quantum mechanics into the same formal structure, but it comes at a cost. The theory allows an enormous number of possible solutions corresponding to different ways the extra dimensions can be shaped. This so-called landscape problem makes it difficult to extract unique, testable predictions. Despite decades of work, string theory has not yet produced experimental confirmation. Another major approach is loop quantum gravity. Instead of introducing new dimensions or objects, this framework takes general relativity seriously and attempts to quantize space-time itself. Space is no longer continuous. It is made of discrete units, linked together in networks. Areas and volumes come in smallest possible chunks. Time evolves in jumps rather than flows. In this view, space-time geometry is granular. At large scales, the granularity is invisible, and space-time appears smooth. Near singularities, the discrete structure becomes dominant, potentially preventing infinite curvature and resolving black hole and Big Bang singularities. Loop quantum gravity does not require extra dimensions and remains closely tied to general relativity. However, it has its own limitations. It does not yet incorporate all known particles and forces into a single framework. Its connection to observable physics remains incomplete. These approaches are not competitors in the usual sense. They represent different intuitions about what must be sacrificed. String theory sacrifices simplicity of spacetime in favor of unification. Loop quantum gravity sacrifices continuity of spacetime in favor of background independence. Both aim to preserve consistency, but they start from different premises. What unites them is the recognition that spacetime cannot remain classical at the deepest level. Whether through strings, loops, networks, or something not yet imagined, spacetime must acquire quantum structure. The search for quantum gravity is not driven by curiosity alone. It is forced by observation. The universe began in a state where quantum effects and gravity were both dominant. Black holes exist where quantum fields and extreme curvature coexist. Ignoring quantum gravity means accepting that our theories cannot describe the most important moments and objects in cosmic history. And yet direct experimental access to quantum gravity is extraordinarily difficult. The characteristic scale at which quantum gravity becomes strong is the Planck scale, far beyond the reach of current particle accelerators. Gravitational interactions are too weak to probe directly at quantum scales. This forces physicists to be indirect, relying on theoretical consistency, mathematical clues, and subtle observational signatures. This difficulty has fueled speculation that gravity itself may not be fundamental. It may be emergent, arising from underlying quantum information or entanglement. In such pictures, spacetime geometry is not primary. It is a collective effect, much like temperature or pressure. Gravity would then be a macroscopic phenomenon, not something to be quantized in the usual sense. If gravity is emergent, the failure to quantize it directly would not be a problem. It would be expected. Quantizing gravity would be like quantizing waves in a crowd without acknowledging the people beneath. This idea remains controversial, but it has gained traction because it offers a way out of the stalemate. It reframes the problem. Instead of forcing gravity into the quantum mold, it asks whether spacetime itself arises from quantum rules that do not look geometric at all. Whether this is correct is still unknown. What is clear is that gravity resists assimilation. It refuses to behave like other forces. Its weakness, its universality, its geometric nature, and its entanglement with time all point to a role unlike anything else in physics. The war between general relativity and quantum mechanics is not a failure of either theory. It is a sign that both are approximations to something deeper. And the deepest hint may come not from forces or particles, but from information itself. Because when physicists study black holes through the lens of quantum theory, they encounter a surprising pattern. Information appears to scale not with volume, but with surface area. Degrees of freedom behave as if reality is encoded on boundaries rather than in space. This strange observation suggests that gravity may not be fundamental at all, but an emergent bookkeeping rule governing how information is organized. If that is true, then the conflict between gravity and quantum mechanics is not a clash to be resolved by force, but a misunderstanding to be dissolved by perspective. And that possibility leads directly to the final turn in this story, the idea that the universe itself may be holographic, and that gravity is not a force or a field, but a shadow cast by deeper quantum information. By the time gravity has carried us this far, something extraordinary has happened. Gravity has dissolved as a force reappeared as geometry fractured. Time vibrated across the universe, lost to dark energy on cosmic scales, collapsed space-time inside black holes, and refused to be quantized like anything else in physics. At this point, the problem is no longer how to fix gravity. The problem is whether gravity was ever what we thought it was at all. The final turn in this story begins with a quiet but devastating observation that emerged from the study of black holes. When physicists examined the thermodynamic properties of black holes, they discovered something deeply unnatural. The amount of information a black hole can contain, its entropy, does not scale with its volume. It scales with the area of its event horizon. Double the surface area and you double the information. Increase the volume inside, and nothing changes. This violates everything we expect from ordinary physics. In all familiar systems, information content grows with volume. More space means more room to store states. Black holes refuse to follow this rule. They behave as if everything that happens inside them is encoded on their surface. This was not a philosophical claim. It emerged from precise calculations linking gravity, thermodynamics, and quantum theory. Black holes obey laws of temperature and entropy. They radiate. They carry information. And that information seems to live not where the matter is, but where space-time closes off. Once this realization is taken seriously, it spreads far beyond black holes. If the maximum amount of information in a region of space depends only on the area of its boundary, then volume may not be fundamental. Space itself may not be fundamental. What we experience as a three-dimensional world could be a projection, a reconstruction, a shadow cast by degrees of freedom, living on a lower dimensional boundary. This idea is known as the holographic principle. A hologram stores a three-dimensional image on a two-dimensional surface. Every part of the surface contains information about the whole image. The depth you perceive is not physically present in the material. It is reconstructed by the way information is encoded. The holographic principle suggests that the universe may work in a similar way. What we perceive as a three-dimensional spacetime could be an emergent description of more fundamental quantum information, defined on a two-dimensional boundary. It is a logical response to the way gravity behaves. If gravity resists, quantization produces singularities and ties information to surfaces rather than volumes, then perhaps gravity is not a fundamental interaction at all. Perhaps it is a bookkeeping rule, a macroscopic effect that emerges when quantum information organizes itself in a particular way. In this view, space-time is not the stage, it is the result. The most concrete realization of this idea appears in a remarkable theoretical correspondence discovered in the late 20th century. In certain simplified universes, a theory of gravity in a higher dimensional space can be mathematically equivalent to a quantum theory without gravity living on its lower dimensional boundary. Every gravitational process in the bulk spacetime corresponds to a quantum process on the boundary. Curvature, motion, black holes, all of it is encoded in quantum interactions that contain no gravity at all. This equivalence is exact in those models. Gravity disappears, replaced by quantum information. The implications are staggering. If gravity can be fully described as an emergent effect of quantum entanglement, then space-time geometry itself may arise from patterns of correlation between quantum states. Distance would measure how entangled systems are. Curvature would reflect how entanglement is distributed. Motion would follow from changes in information structure. In such a universe, gravity is not something particles feel. It is something information does. This perspective reframes every earlier paradox. Gravity's weakness becomes natural because emergent phenomena are often weak compared to fundamental interactions. The failure to quantize gravity becomes expected because you do not quantize temperature or pressure at the microscopic level. Singularities become signals that the geometric description has broken down, not that reality has gone infinite. Dark energy becomes a property of information balance, not a mysterious substance filling space. Even time itself begins to look less fundamental. If space-time emerges from quantum correlations, then time may be a parameter describing how information reorganizes, not a universal flow. The bending of time near gravity would reflect changes in how information is accessed and updated across different regions. From this angle, gravity stops being an enemy of quantum mechanics. It becomes a consequence of it. This is why some physicists describe gravity as an oracle. It knows something we do not. It encodes quantum information in geometric form, translating microscopic rules into macroscopic structure. As Raphael Bousso once remarked, gravity is smarter than you, not as an insult, but as a warning. Gravity obeys constraints rooted in quantum information long before we understand them. This does not mean the holographic principle is proven in our universe. The evidence is indirect, theoretical, and incomplete. But it is compelling precisely because it unifies so many loose ends. It explains why gravity behaves differently from other interactions. It explains why information matters more than volume, It explains why space-time geometry seems to know about quantum entanglement. Most importantly, it changes the question we ask. We stop asking what gravity is made of and start asking what space-time is an expression of. At the end of this journey, gravity no longer feels like a force pulling us down. It feels like a translation layer between the deep quantum world and the universe we experience. A shadow cast by information. A structure that emerges when reality organizes itself coherently enough to look like space and time. Nothing about this diminishes gravity's importance. If anything, it elevates it. Gravity becomes the visible trace of invisible rules, the macroscopic signature of microscopic order. It is not primitive. It is profound. And perhaps that is why gravity has resisted us for so long. We have been trying to treat it as something it is not. If this perspective is even partially correct, then the universe is not built from space-time and forces. It is built from information and relationships. Space is what that information looks like when it arranges itself locally. Time is what change looks like when information updates. Gravity is how consistency is enforced. At that point, the phrase misunderstood force takes on a deeper meaning. Gravity was never misunderstood because we lacked equations. It was misunderstood because we were asking the wrong kind of question. And now, as this long arc closes, the picture does not resolve into certainty. It resolves into clarity about what remains unknown. Gravity has led us from apples to black holes, from geometry to information, from force to emergence. It has dismantled every assumption we tried to impose on it. If there is a quiet lesson here, it is not about mastery, but humility. The universe does not owe us intuitive explanations. It offers patterns. We learn to read them. Thank you for spending this time here, following this long trail through gravity's many disguises. If these ideas have stayed with you even as the night deepens, that is enough. You do not need to hold on to every detail. The structure remains, even when attention fades. As the screen dims and the universe continues its silent expansion, may your thoughts settle the way space-time does, far from mass open, unstrained and unhurried. Wherever you are listening from and whatever moment of rest has found you, I wish you a calm night and an easy sleep.